Good evening, ladies and gentlemen. I'm Markus Schweiger. As president of the Bavarian Academy of Science, I would like to welcome you all to our Munich AI lecture given by Alexei Efros, focusing on the questions if we are giving data enough credit. We are very proud to host this event. It's a royal residence in the center of Munich, which houses the main office of the Bavarian Academy of Science. Founded in 1759, the Academy functions today as a community of scholars, a non-university research institution, and an interface between the Bavarian scientific community, society, and the policymakers and political decision makers. With its scholars, the Academy provides a powerful interdisciplinary forum of very established scientists. This network of excellence interacts closely with all Bavarian research institutions and political decision makers and represents an important part of the science communication with the public in Bavaria. Research activities range from composer Richard Strauss to the study of climate change in the Alps, from Baroque ceiling paintings to quantum physics. The longer-term basic research spans from natural sciences and technology to humanities and social studies. The Academy projects actively leverage most advanced digital technologies. The Leibniz Supercomputing Center is part of our Academy and serves as an important infrastructure for all Munich universities. Today, we hear an important contribution to the rapidly growing discussions about artificial intelligence from Alexei Efros. He is professor of computer science at the University of California in Berkeley and works in the area of computer vision and computer graphics. Furthermore, he's a member of the famous Berkeley Artificial Intelligence Research Lab. We just heard that it's a very famous envelope for all the activities in the Berkeley area. For most of the computer vision existence, the focus is primarily on algorithms and models. Only gradually, the discipline appreciates organizational and societal challenges to collect high-quality, large data sets. At the Academy, we also focus on collection and utilization of digital health data from Bavarian patients in order to realize the potential of personalized medicine and also encounter a lot of hurdles and obstacles to overcome and to get the high standard quality we need. Professor Efros will focus on some historical examples illustrating the importance of large visual data in human and computer vision. He will then share some of his recent work demonstrating the power of very simple algorithm when used with the right data set, including visual in-context learning and visual data attribution. The AI, or the Munich AI lectures, are a joint initiative of biospheres on all major Bavarian research institutions and institutes active in the area of AI application. This particular lecture is part of a two-day workshop organized by Professor Bernd Ommer. I like to thank Bernd especially for all his efforts to attract all these outstanding scientists from all over the world, and congratulate him. Today was the first day for the success of this excellent meeting in Munich. Thus now I hand over to Michael Klimke, who serves as the CEO of the Bavarian AI Agency and organizes all the activities associated with Biosphere, and wish us all an insightful and interesting evening. Thank you for coming.
Yeah, thank you very much, Professor Schweiger. Ladies and gentlemen, dear guests, dear colleagues from the field of artificial intelligence, it's my great honor to welcome you today to this special talk by Professor Alexei Efros. I'm delighted to see so many brilliant faces and minds here in the auditorium, but also in the live stream. I actually can't see them, but I know that they are there. We're all united because we share a passion for advancing AI research and technology, especially in this vibrant ecosystem here in Munich, in Bavaria, which is called Biosphere. My name is Michael Klimke. I'm the head of the Bavarian AI agency, and our role is given by the Bavarian state government to promote this excellent network and to make it visible under the label of Biosphere. It's an amazing network of brilliant minds and institutions supported by the high-tech agenda of Bavarian state government, a program worth 5.5 billion euros, not only for AI, but other high-tech fields. And the Biosphere, the network, consists of over 900 professors all across Bavaria that are active in the field of AI. They work at more than 40 universities, but also at Fraunhofer, DLR, and Helmholtz institutes. And it's more than 30 AI study programs that have been established there with thousands of students all across Bavaria. There's also transfer programs, private investors, companies, from startups to SMEs and world-class enterprises that operate in Bavaria and all across the world. So tonight, Biosphere presents the Munich AI lecture. As Professor Schweiger has said, this lecture series is a joint effort by the Bavarian Academy of Sciences and Humanities and with its Bavarian Research Institute for Digital Transformation. Thanks for having us tonight, for hosting this event. But it's also an initiative by the Helmholtz Munich Center, by the Ellis Chapter Munich, and both large Munich universities, the Ludwig Maximilian University and the Technical University of Munich, with their research hubs and institutions like the AI Hub at LMU, the Konrad Zuse School of Excellence in Reliable AI, the Munich Center for Machine Learning, the Munich Data Science Institute, and the Munich Institute of Robotics and Machine Intelligence. Our vision for the Munich AI lecture is to create a dynamic environment and a collaborative format for the knowledge transfer and exchange between leading AI researchers from all across the world who share their latest breakthroughs and their latest ideas, and to promote these ideas and to establish a dialogue with the researchers and especially the young researchers and also the students here in the greater Munich area. The Munich AI lectures bring the big shots of AI to Munich. I can refer to Jan Lequin, who has been standing here last year. Great success. It's over 75,000 views on YouTube in the meantime, so really a landmark event for the Munich AI lectures that set the tone for what is to come now. Just 2 days ago, we had Professor Daniela Roos from MIT CSAIL lab here. She gave a captivating lecture on liquid neural networks. Awesome to have her here, and she's also a member of the Bavarian AI Council that is advising the Bavarian state government on issues of artificial intelligence. We have many more talks to come this year, so please have a look at our website and feel free to join us also for the next events. Spread the word, because your participation in this effort is vital. As researchers, as innovators, as advisors, we are all part of Biosphere, and only together we can shape the network to become a beacon of excellence in AI within Germany, Europe, and beyond. With this, I want to hand over to Professor Björn Ommer, who has been organizing the workshop this day and tomorrow, and he's been also organizing this event tonight. You might know Björn Ommer, that he and his team, he developed a stable diffusion model He's a professor at the LMU University. Before that, he was also in computer vision at the University of Heidelberg, and his academic career led him also to Zurich, to Bonn, and UC Berkeley. He's a member of many institutions, also a member of the Bavarian AI Council. And with that being said, Björn, I would like to ask you to come and to introduce also our speaker. Thank you very much.
Thank you, Michael, for the kind words. Ladies and gentlemen, esteemed colleagues and distinguished guests, it's my sincere pleasure to welcome you to this AI lecture, this Munich AI lecture that we're having now, which is at the same time also the evening keynote of our international workshop on open problems in computer vision and generative modeling. Generative AI has, within the last 2 years, developed from for most of the society, obscure discipline focused on generating some cat images to the enabling technology that pretty much propels all of our industry, research, and permeates all of society. It's been driven by algorithmic development, it's been driven by compute, but in particular also by data. And I'm delighted to introduce to you a speaker whose career has been focused on this triplet, and especially on data, like no other, Alyosha Efros. He gave his talk the title, "We're Still Not Giving Data Enough Credit," and I guess that's the name of the game there. He received his bachelor's from University of Utah and then went over to beautiful Berkeley, where he received his master's and then his PhD degree, supervised by Jitendra Malik. He afterwards spent a postdoc in Oxford with Andrew Zisserman, then started as an assistant and followed by an associate professor at CMU in Pittsburgh. And because he couldn't stand living there or wanted to go back to the West Coast, he started in 2013 as first associate and now full professor at ECS of UC Berkeley and is part of the Bear Lab there. Alyosha has also a lot of ties to Europe, collaborations with Paris, UK, and lots of other places. He's been recipient of numerous Best Paper Awards, 3 Pami Helmholtz Test of Time Awards, awarding him for research that really stood the test of time, and the distinguished Thomas Huang Memorial Place, and above all, also the prestigious ACM Prize in Computing. Alyosha's highly influential research has since his PhD been about using vast amounts of unlabeled visual data to understand, model, and also to recreate our visual world around us. His work has left an imprint on computer vision, graphics, computational photography, and many other fields. But in particular, it has for long pointed out the value of large amounts of unlabeled data, in particular images, over tedious annotations or complex machine learning methods, both of whom our beloved Jitendra actually called mumbo jumbo, and he wanted to find other ways around. Rather, Alyosha has been on a mission. I guess that's the way to coin it. A mission to prove that the humble nearest neighbor classifier, simplest machine learning approaches, if fed right and with the right data, can outperform overly complex machine learning approaches and also tedious annotations. But above all, Alyosha is, however, not only a great and influential scientist, an inspiring speaker, which you for sure going to notice over the next couple of minutes, but also a dear friend to many in our community and great fun to be with. Alyosha, welcome on stage.
Thank you very much for way too generous of an introduction, and I would like to thank the Bavarian Academy for hosting us, and to Björn and the Alice Network for this wonderful workshop that we're having with so many brilliant, wonderful colleagues. And so it's a little bit of a complicated mission for me, because I want to make this entertaining and understandable to more broad audience, but also give the luminaries of the field, a few nuggets that they can also appreciate. So let's see if I manage to do this. I've been talking about the importance of data for a very, very long time. Really, this is like idea fix of mine since graduate school. So I thought, do I really need to talk about this again? And then this document started making the rounds in around San Francisco with a lot of my students and other folks at Berkeley reading this. And so this is a post quite long from somebody who just left or maybe got fired from OpenAI, talking about all the scary things that are going to happen. And you don't need to read it because I made a little Wordle. So here is the kind of what it really talks about. It's, models, GPT, AI, compute, progress, year, researchers, right? And what caught my eye, though, is that where is the data? Tiny little thing over there. And so I thought, okay, maybe I should talk about data still, okay? So let's start, but yeah, because really I feel like much of the magic is in the data, okay? I mean, it doesn't mean that it's all just the data, but data really deserves a big chunk of the credit. I think hopefully I'll be able to prove it to you in the next hour. So let's start in Paris. Okay, this is Gare Saint-Lazare. If you go 6 hours by TGV, you're in Musée d'Orsay. Wonderful painting. I really like it. It's really kind of gets you into the frame, the hustle and bustle of this train station, and you feel like you're there. The fumes of this steam engine as it's entering the view and it's coming directly at the viewer, right? The steam engine. Does everybody see the steam engine? Yes. Oh, look at this. Is it a steam engine? Or is it like a splotch of paint on a canvas? Or maybe like a bottle stuck in a cooler? Or maybe a penguin? Where is the steam engine? Because it's not in the pixels. Well, the steam engine is in our memories. And I bet that each of you sees a slightly different version of the steam engine depending on which steam engine museum you went to as a child. Okay? So this is very, very important. We are really, really good at seeing not just with our eyes, but also with our memories. So this is a beautiful video made by my dear friend Antonio Torralba. This is Rob Fergus in his youth working on his computer somewhere at MIT. And even though the video is very, very blurry, you have no problem understanding what's going on, right? In fact, maybe it's a little bit, you're seeing too much, because here you see that Rob is talking on his shoe, and now he's going to work on his trash can, listening to his Coke cans, and look at the mouse here and the printer, right? It's the memory that commands the story. Moshe Bar says, our perception relies on memory as much as it does on incoming information, which blurs the border between perception and cognition. Lance Williams says, mind is largely an emergent property of data. Now, given that, historically, data has really not got much respect especially in the machine learning circles, because it was all about the algorithms. You come up with a really, really smart algorithm, very clever. You work on it for half a year, you write it up, and then maybe a week before the NeurIPS deadline, you add some features, and then the night before you run it on some data, you submit a paper, you get an oral, and then everybody's happy, right? That was the story for a very, very long time. And the problem is that this kind of thinking obscures some important issues. So let's kind of start from maybe early days. So this is late 90s. This is when I was a graduate student. And in computer vision, it was very depressing to be a graduate student because nothing worked. It was really just nothing worked. And then magically, face detection started to work. I remember that was such an exciting moment. Suddenly, we could detect faces. And then like in a couple of years, it was in all the cameras, and it was maybe one of the early big successes of computer vision. And for those of you who took machine learning class or computer vision class, what was the one paper that made face detection work? Can anybody tell me? Viola and Jones, thank you very much. That very reliable audience. Actually, the right answer is that there were 3 papers, okay? Raleigh, Beluga, Kanadi in 98, Schneider, Kanadi in 99, and Viola and Jones in 2001. All 3 are very respected, very well cited. All 3 got the Test of Time award. And yet, we all collectively remember Viola and Jones. And even if you look at the latest, greatest vision textbook by Taralba, Isola, and Freeman, that's the only one they actually mention. So why is this? Well, if you look at Raleigh was the first one, okay? Schneider was the best performing one. Viola Jones was the first real time, although I think by that time Schneiderman already made his real time as well. But what else is different here is that Raleigh, the algorithm was very boring. This old school stuff called neural networks. It was kind of embarrassing to be doing neural networks in the 90s because it was like stuff you did in the 80s. So, it was kind of embarrassing. Schneiderman, okay, maybe more interesting, but, the classifier naive Bayes, kind of naive, not that exciting. Viola and Jones, boosted cascade. It's a beautiful algorithm. When I teach machine learning class, I still talk about it because it's an absolutely gorgeous, very clever algorithm. But was it the thing that made it work? I don't think so. In fact, what made all of these 3 papers work really well was this was the first set of papers that realized that you needed data not just for the faces, but also for the non-faces. This was the first time people started using negative data. And that's really what made them work. And yet, we're still, remember the boosted cascade. So I call this kind of our scientific narcissism. That given everything else being equal, we prefer to credit our own cleverness. We prefer to say that it was our cool algorithm that made it work, rather than admit that, okay, maybe it was the data that is, it's not clever, it's just there, okay? But I think this has led us in the wrong path a number of times, and if we're not careful, it will lead us astray in the future. Because data is really, really powerful. So there is this wonderful paper from 15 years ago called The Unreasonable Effectiveness of Data. And basically the argument in this paper from folks in Google is that much of our world can be explained by elegant mathematics, physics, chemistry, astronomy, etc. But there is some things that it doesn't seem to be able to. Things like psychology, genetics, economics, AI. And these are all things that are kind of connected to evolutionary processes, right? These are all areas where evolution plays a big role with its injection of randomness, injection of entropy. And these are exactly the fields where we are observing the magic of data, okay? And this is maybe not that surprising because, let's say, you are a computer graphics company and you want to do special effects for a movie and you want to synthesize smoke. Well, actually, smoke is very easy. It's because we have known how to synthesize smoke for 20 years. Just plug your Navier-Stokes, some parameters into your Navier-Stokes and run your physics simulator, and you get beautiful, beautiful, gorgeous smoke. Okay? We have been able to do it for 30 years. But let's say that you want to simulate the pattern of bark on this tree. Okay? Now, there is no closed form solution, not a compact one at least, because the pattern of bark on this tree depends on a lot of things. It depends on the genome of the tree. It depends on the location of the tree, the weather, whether there was a squirrel nesting in this tree. A lot of parameters go into the particular pattern, And a lot of those things are just random. It's just raw entropy that makes the tree look like a tree. And these are exactly the kind of phenomena where instead of trying to have an explicit parametric model, you just take lots of pictures of trees and interpolate between them. And essentially that, I would argue, what a lot of the data-driven methods are doing. Okay? And luckily, we have a lot of data nowadays. And so there's so much data that even the brain-dead methods, technically known as nearest neighbor approaches, they work surprisingly well. This is probably the most important computer vision paper of the last 20 years. And you know that it's important because it got rejected from all 3 major computer vision conferences. It is an amazing paper by Torralba, Ferguson, and Freeman, where the authors asked the question, how many images on average does a 5-year-old see in their life, in their 5 years of life? And their back-of-the-envelope calculation is about 80 million. And they said, well, 80 million is not that huge. Like, maybe we can just capture that much data. Now, back, because it was 2008, they didn't have enough disk space, so they made those images very tiny. They made them 32 by 32. But they had 80 million of those images. And in a very weird, crazy, perverse laugh of history, nobody seems to remember this paper, but everybody remembers CFAR 10 and CFAR 100, which was a tiny, tiny sliver of this 80 million data set. So a lot of machine learning progress was done on minuscule data that for some reason, they decided that that's all the data they needed, okay? But this paper was really, really very powerful because it basically showed that, look, if you have enough data, then any new image you're going to have is going to be quite similar to what you already have seen. So this is the nearest neighbor. Find the closest thing to what you already seen, or maybe the K closest things. And it might be pretty good. And this paper already had things that, like WordNet, hierarchies, and all that stuff that later would show up in ImageNet. This paper already had it. And basically, you could even do some sort of recognition by essentially, taking an image, looking at the nearest neighbors, and then having those nearest neighbors vote on entries in the WordNet hierarchy, and then it could basically figure out, okay, this is a person and it's a worker, and basically have some way, very simple way to figure out what is in this image just by using the data. At the same time, my former student James Hayes and I were playing around with lots of data for the generative side of the story, and we were thinking about things like, okay, what happens if you want to remove this building and want to still have a nice image, so how do you fill in the hole? The same idea. Download tons and tons of images, 2 million images in this case, find the nearest neighbor, and a little bit of computer graphics magic, fill in the hole. And it just kind of magically works. We had a follow-up paper we called Im2GPS. We said, you know what? You can also do nearest neighbors and steal the labels from the data. So we said, okay, what if we have an image and we want to know where on Earth was this image taken? Easy. We download now 6 million images, but also associated GPS tags from those images. And now we get a set of nearest neighbors and have them vote on the map of the Earth where they think is the most likely place for this image. And in this case, they're basically, a lot of them are agreeing that it's somewhere in southern Utah, which is, in this case, is correct, okay? So now, fast forward 15 years, neural networks come into the scene, and some folks from Google decide, okay, we're going to replicate the study, but now with a much more powerful method, inception neural network, and also, of course, they have much more data, okay? And they got much, much better performance. But luckily, I was the reviewer for this paper. And so I said, wait a minute here. You're changing two things here at the same time. So now you're going from nearest neighbor classifier to a deep network, but you're also getting your much more data, an order of magnitude more data. How about we look at apples to apples comparison? And the authors very kindly provided one. And now, at this, here you can see that with the apples to apples comparison, the fancy schmancy deep network from Google is basically not doing much better than the simple nearest neighbor classifier. And indeed, for some regimes, it's doing a little bit worse. Okay? Now, I'm not saying throw away your neural networks and go back to nearest neighbor, but what this shows is that for this particular problem, what the neural network needed to do is just to be a fast nearest neighbor classifier. It did not need to do anything smarter than that because the smarts were already sitting in the data. And I think we have to really kind of remember this kind of settings where the algorithm often gets the credit where data might be the better place to give credit to. Okay? So the good news is really stupid algorithms plus lots of data gives you this unreasonable effectiveness for many of the problems. But a very natural question is, okay, we're trying, artificial intelligence, we're trying to maybe understand how natural intelligence is also working. Surely humans cannot remember that much data. This whole big data thing is for computers, but surely humans cannot do this. Well, luckily, there is a wonderful series of papers from Odd Oliver's lab, and she actually was interested in this very question: how much visual memory? What's the capacity of the human visual memory? And she very kindly lent me her slides, and we are actually going to try to do a study that she did. So basically, what was known since the 70s, there was a work by Standing who showed that actually humans are surprisingly good at remembering visual data, okay? About 83% for 10,000 images, okay? But what was not clear is all these images that Standing showed to his subjects were very, very different. So there was one of kitchens, and there was one of beaches, and there was one of forests. And so it wasn't clear, were the people just remembering a few keywords? Were they remembering some kind of sparse detail? Or was it like really super detailed, almost like, picture perfect? So that wasn't clear, and this is what Odd decided to study. So she basically showed her subject a series of images, and in some of those images were just very different object categories. Sometimes it was the same object categories, just different instances, and sometimes it was the same category, same instance, but a different state of the object, okay? And then she wanted to see how were the recall for all of these tasks. So this is the participatory part of the talk where all of us are going to perform the study, okay? So the task is, first you're going to notice if you have seen an image before and clap. And then at the end, we're also going to show you pairs of images, and then you're going to tell me which one you have seen and which one you have not seen, okay? So every time you see an image you have seen before, you're going to clap. Ready? Okay? Ready? Okay. Okay, it's going to go really fast. So ready? Okay, let's do it. Okay, I'm going to fast forward a little bit. Okay. So I think now you're starting to guess what's going to be the outcome, but let's also see how well did you guys do. A or B? Very good. A or B? Oh, wait, how many A's? How many B's? Okay. Very good. A or B? Very good. Okay, so how did we do? Well, these are not us, this is the odd subjects. So for the novel categories, it basically was better than standing, replicating standing, and also actually doing even better than 92% recall, okay? But the question is, how well did it do for the much more hard tests? And I think you're gonna not be surprised, barely no loss of performance on those two. Okay, and this I think was very, very interesting for a lot of us to see that actually we humans are very good at remembering a lot of visual data, and maybe that shouldn't be an argument against not using it. Okay, so okay, this simple methods, raw memorization, nearest neighbors, they're great, but they have trouble with rare events, the proverbial long tail, right? Where there are many things that you just never seen before, right? And this is where the old nearest neighbor methods really had trouble with. And this is exactly where the modern generative models are doing really, really impressive work, because they're able to interpolate and compose data from different sources. And things like DALL-E, Stable Diffusion, thank you Bjorn, and other methods like that, they can do things that really have never been seen before, like a dolphin in an astronaut suit on Saturn. You know, this is, obviously there is nothing like that in the training set, right? So this is really, really exciting. But I'm worried that maybe we are getting a little bit too excited again about the wrong thing. Because yes, it's all about amazing algorithms and the fancy language features, and oh yeah, and there is also some data, right? But maybe we should really revisit this. So here is a standard image, text-to-image model. I gave it a prompt, squirrel reaching for a nut. And here are 3 results. Now these 3 results are 3 different models. Now, you might have your favorite here, but all 3 seem to be doing reasonable performance. And the first one is diffusion-based, the second one is autoregressive, the third one is GAN-based. So algorithmically, those 3 models are very, very different, extremely different. But they're all doing reasonably well because they're trained on very similar data, okay? And there is even this beautiful plot that Tae-Sung Park, my former student, generated that shows the quality of the images produced by the models as a function of the model capacity. How big is the model? How much data it can absorb? Now, the quality is in this metric called FID, which has some problems, but I think there is still a kernel of truth here that basically it doesn't really matter that much what the algorithm is. What really matters a lot is the capacity of that model. How big, how many parameters, how much data it can absorb. With the more data it's able to absorb, the lower the FID, the better is the results. And I think I suspect this is going to continue, and we'll have more and more interesting methods. But all of these methods, I think, are going to be very, very large, able to capture a lot of the data. Okay? Still, it's really, really impressive that you can take an image, take a prompt, something crazy like a green creature made of leaves and vines bursting out of ground, ready to attack, really creative stuff, and it will give you something really cool. This is Bjorn's Stable Diffusion, very Very, very evocative, really cool. And it's this looks magical, right? And it also kind of feels like, okay, it seems to be doing something really creative because, how many weird creatures are there in the training data? Now, on the other hand, nobody really has seen all the training data. It's like 5 billion images, right? So we have a little project on trying to do what's called data attribution, where we try to find the few images, real images from that 5 billion image data set that are most influencing the synthetic image that's being generated. And I'm not going to talk about how that paper works. It's actually pretty standard. But here are the top 6 most influential real images that were used to generate this generated image. Okay? And it's kind of interesting, right? Because I didn't realize that first that these kind of synthetic images are in the Lion data set, in the big data set that was used. And second, that okay, it's definitely not copying images from the training data. But it's maybe not that crazy to imagine some way to interpolate between these kind of images to get you something like this generated image. At least it definitely looks maybe a little less magical and a little bit more believable now that we know what the real data and what the real relevant data looks like. So I like to paraphrase Arthur C. Clarke. Interpolation in sufficiently high-dimensional space is indistinguishable from magic, right? Because we can think about interpolation in 1D, maybe 2D. By the time we're in 3D, it's already getting a little bit hard to imagine. And this is, a very, very high-dimensional space where this is being interpolated. So it might be that the process that's being performed in the end will turn out to be not that mysterious after all. It's just that it's relying on a huge amount of data. And in fact, it could be that our visual space maybe is not as huge as a lot of us in computer vision have thought. And kind of maybe some hint about why this might be comes from some work from the 90s. So in the 90s, there was a lot of work on modeling faces using linear subspaces, okay? And there were some really amazing results. You take a few hundred face images, and it turned out with the right magic and the right key point alignment, you could basically generate any other face as a linear combination of these few hundred input images, right? And one of the classic papers is Blanson-Vetter, which showed really that you basically can, with 200 German graduate students as input points, you can have a linear space that basically models everyone. All of us could be modeled by 200 German graduate students. It was really, really shocking and basically kind of suggested that, there might be more people on Earth than there are faces, right? That the space of, all of us, and we have seen some evidence of that now from all these companies like Facebook and Google, that, we all have about, a couple of hundred of doppelgangers because the space is maybe not that crazy high dimensional as we thought. And that just by simple linear combination, we can get to a lot of it. So knowing that, we got to think, we could do linear latent subspaces using faces from the 90s, or using latent vectors from like the GANs from 5 years ago. But what if we do linear spaces of actual diffusion models, the weights of the diffusion models? So we could think of a data set of models and try to do a linear subspace within that data set. And this is what we did here. And the idea is you get yourself a whole bunch of networks, a whole bunch of basically stable diffusion networks. And then you see what happens if I interpolate to create a new network that can, for example, generate pictures of me. right? So it's not generating an image of me. It generates a network that can generate infinite numbers of me in different places, even though I was definitely not one of the people that it was trained on, okay? So it's kind of like you're generating a new network without having to ever run backprop. You just linearly interpolate between the images, the networks that you already did, right? So basically the idea is we take a stable diffusion network, pre-trained network, and then we fine-tune it for the task of generating a particular person. So we basically do custom diffusion for a set of training images of a particular person, and then we have a whole bunch, a whole family, a database of networks that can each generate a particular person, okay? And now we take the weights of that network, and we can populate the weight space of all those networks, and we have basically 60,000 of them. So it's a huge data set of networks, but we can basically project them all onto a linear subspace, and now we can reason about it as any kind of linear subspace. So we can put it together. We call it weights-to-weight space. And now you can do all the things that you used to do with PCA. For example, you can sample from that space to generate a new network that produces a new person that was none of the training people that we had in the training set. So here are some sampled identities, and these are the nearest neighbors through them. You can see that the nearest neighbors are quite far, so it's actually a new person. We can also do some editing. So for example, if we have some labels that says people that have mustache, people that don't have mustache, we can now, or beard, we can now take a particular model and push it towards having a beard. Voila, now we changed it to a new model that produces the same person but with a beard. And notice that other people that is not that person are not affected. So it's just for that particular person, okay? Or we can invert a novel image into that linear latent space. For example, we can take a painting here and try to represent it as a linear combination of weights of our 60,000 models. Now, all those models are real images. This is a painting. So it's basically projected into a model that can produce images of a real person most similar to that painting. And I think it's doing something. It's not unreasonable. Here are some more inversions. This is an input image, and these are some of the model's outputs for that real people. And then we also can do things like, how they say that the owners and the pets look similar. So here is an input of a dog, and it says, okay, projected onto a space of faces, and this is the person most similar to this, and this is the same thing but with a sketch. And we can extend it to other domains, for example, dogs, and it still works. So this is just a little kind of a toy teaser to show that it seems like maybe there is other ways we can generate models other than backprop by doing some linear combinations. Okay, so it's interesting to think about this lots of data and think about, can the availability of data really predict the success of a particular set of AI models? And I think it can. For example, let's take the largest data available right now is text data, right? And models like GPT are the best performing models right now. The second largest data is images. And the text-to-image models are working pretty well. Then comes something like video data. There is really not that much video data right now available. And so models like Sora, they're not working as well. And then the last, of course, is robotics, which essentially there is no data, and so it just completely doesn't work. Okay? So this is maybe there is a pattern here. And in fact, I think that this we are seeing here is a bit of a return of Moravec's paradox. So for those who don't know, Moravec's paradox is basically saying that in AI, the hard things are easy and the easy things are hard. So for example, here is a picture of Garry Kasparov losing to Deep Blue about 30 years ago, right? 30 years ago was the last time human beat a machine in chess. But even now in 2024, we still need to have a dude moving the chess pieces. There is no robot that can actually move reliably chess pieces on an arbitrary chessboard, right? So this is kind of a classic example of Moravec's paradox. And just recently, there is an archive paper that kind of shows kind of a similar thing happening with all of these large vision language models, which they can do these beautiful, beautiful things. But for the simple question of how many times does the blue and the red lines intersect, they're basically not doing well, okay? So again, another example of Moravec's paradox. And also, I think kind of looking forward, you know, how much data are we going to have? You can say, okay, well, obviously we just need to create more data, so we just need to add more data and everything will be good. Well, the problem is that in terms of text data, I think we're scraping the bottom of the barrel here, because we've been using 2,000 years of human cultural history, and we're basically done. Now, whatever is left is Twitter and Reddit, and that's not going to be high-quality data, okay? It's not going to be Shakespeare. So I feel like we're going to be running out of text data soon. In comparison, the data that comes from low-level signals, like visual data, robotics data, sensory data, those reserves are, to my mind, they're basically infinite. We can just keep getting more and more of that data. It's not going to be as high quality data, it's going to be very noisy data, it's going to be very low level data, but there is infinite reserves of that data. So I feel like the focus is going to start moving downward into this kind of a more low level kind of data. And it makes a lot of sense, because if you look kind of historically, evolutionary, the progress, was, Cambrian explosion, where it was when we had vision first developed, then, manipulation, and only basically, 5 minutes ago, evolutionary speaking, is when we started to have language. And, all animals on Earth can see and manipulate and navigate and manipulate, and only one of those animals can speak. So it seems like we are really, it would make sense to think about an alternative to this kind of a top-down learning, where we start with language, start with this kind of a, kind of almost like a creationist idea of, you get the high-level concepts and then you go downwards, and maybe consider something that's much more bottom-up. You start with the low-level signals, the pixels and the torques and things, and then try to boot yourself up from the bottom to the top. Kind of this bottom-up emergence. And this is the kind of things that I'm currently very interested in. And so I'm gonna, in the next little bit, I'm gonna show you some of our most recent works. And this. One is this work on visual prompting. So, of course, we're very, very jealous of the language people who can do this prompting. You don't need to have a task. You basically just say, give a prompt to say, okay, English and French, and then a sentence in English, and it understands that what you mean is to translate it to French. Can we do it with visual data? Well, actually, maybe we can, because what is this prompting in terms of another way to think about it? It's basically an analogy. If you remember from some standardized tests, A as to A prime is B as to what, right? And in fact, Aaron Hertzman, 20 years ago, published a wonderful, very influential paper called Image Analogies that basically tried to solve this problem. But the point here is that actually a lot of computer vision tasks could be formulated in these kind of visual prompts, okay? And you could you could see how well you can do trying to solve this task without specifying ahead of time what are the, what are you going to be asking the computer to do, okay? And so we said, okay, let's try to do a new version of this kind of image analysis visual prompting. And the thing is that the solution that my students came up with is really, it's the dumbest thing ever. And if they told me ahead of time, I'd say this was never going to work. But it did. So there's a solution is you take your 4 images of this analogy, you put them all into one bigger image, and then you just whole fill that thing with a standard in-painting model, in this case, a version of a must-out encoder. Okay? And because of the data that it has seen, that the in-painting model has seen, especially because we trained it on grids of images, it basically figured out some sort of symmetry-based analogies that would make sense, and it basically figured out how to do, in this case, a segmentation task, okay? And here is some other tasks that it was doing reasonably well, and, even though we didn't tell it anything about what the task was, we just gave it this triplet of images and, told it to let it rip, okay? And we also tried it on some synthetic images, and it was doing reasonably well. I was super, super shocked that such a simple thing would do okay. And of course, it doesn't. It's not going to beat any records. It's not going to be perfect. There's definitely things that it cannot do, and often, 1 or 2 exemplars is just not enough to specify a task anyway. So it's not the answer to everything, but the fact that it's doing something to me felt very interesting, especially since there was absolutely no language here, no semantics. It was just low-level signal, and that's it. Okay? So I was very, very excited. This was, I guess, a year and a half ago, and I thought, okay, let's scale it up. Let's just hit it with all the visual data that we have, and that unfortunately did not work at all. Because the must-out encoder, as it turned out, just doesn't seem to scale well. It's the capacity thing again. So no matter how much we tried, it just did not have the capacity somehow to absorb more data. So the performance basically just stagnated. And this is where we decided to just, go all out and join the masses and try it with a autoregressive sequence model like the standard large language models, okay? And this is a paper from this year's CVPR. But the idea is we're going to use the tools of large language models, but not using any language. So there is absolutely not a single word, not a single letter in this whole project, okay? It's all just pixels. So basically, we formulated the data as if it was sequence of tokens data, but it's all pixel data. So we came up with this idea of visual sentence, and visual sentence could be just one image. And basically, in this case, we just generate from a single image, we generate it as a sequence of tokens, about 256 tokens per image, okay? And that's basically our visual sentence. Or it could be a snippet of video. In this case, it's a sequence of frames and then end of a sentence token. Or it could be a set of images of rotated object, for example, something like this. Or it could be, one of the ImageNet categories, or it could be an image followed by a notation, and another image followed by another annotation, etc., etc. And basically, all the data sets we could get our hands on, we just fed it into the system as a sequence of these visual tokens, okay? And that basically, we just took all of the data, about 420 billion tokens, and we just fed it into Llama, into standard large language model. So it's basically using the standard text-based machinery, except now the data is visual, okay? And once we trained it, and it of course took a very long time, now we can prompt it with the kind of natural kind of prompting of, okay, here is some context, what comes next? So in this particular case, what comes next should be probably the next frame in this video, and indeed, that's what it's able to do, okay? And in fact, we can even make it generate several frames of that video, and it seems to be doing okay. Okay, so here are some examples. Now, of course, the capacity of the model is much smaller because images take much more tokens than words. So you can't do too far, but it's able to predict sequences of object rotations, again, without specifying any kind of task. Just by prompting it with a sequence, it says, okay, I know what you want from me, I'm just going to continue generating. Or we can do what we call analogy prompting. So we can say, okay, image, body plan, image, body plan, image, body plan, image. Now it's your turn, model. And the model is like, I guess you want me to do a body plan. Okay, here you go. Again, no task or anything specified at all. And no language. So here is a bunch of various prompts and the generated images. So here, basically, all the first few prompts is just to get it to figure out what task it's doing, and the last image here is the one that is actually we are trying to actually solve. Okay, thank you. And now all of these things, of course, it has seen at training time. So it's kind of nice that it's remembered all of these things, and nice that it can kind of generalize to different examples of the same task. So the images are different, but the tasks are the same. But what about a task it has never seen at training? Or maybe some sort of compositionality. So here we say, okay, here is an object that is being rotated, but I'm also going to label key points on the wheels. Okay? And now I'm going to give a new object and label the key points, and I want you to continue the pattern. And it figured out that you wanted to keep rotating the car, but also keep labeling the key points as well. Okay, and it seems to be able to compose these two tasks. Okay, here is another task that has not been seen at training time, like lighting change kind of task, or things that we don't even know what the right answer is, but looks okay. Okay. And then we also tried it on something that in the 30s, this was kind of a big thing for measuring non-verbal IQ tests. The idea is to find here's a pattern, this kind of Raven progressive matrices, and the question is like, what should go into the empty hole? And we go, okay, well, this kind of hole filling task. Let's see what it can do. And so here is some holes, and here are some of the successes of the method, and you can see that it seems to be doing something, although we also have plenty of examples where it did not work well. And in general, this approach has many failure modes. It's definitely not something that you want to use right away, although we have the model and the code online if you want to. This is not even GPT-2. This is like GPT 1.2, right? It's probably the biggest computer vision model, but as far as language models, it's tiny. Okay, so there is still a lot to push to see what can it do in general, but we want to push in this direction. We want to go from the pixels upwards rather than from language down and see how far we can get. Okay, so in summary, I believe that bottom-up invergence of intelligence from raw sensor data is a worthwhile research goal, especially for those of us who are in academia. If you're in industry or if you're in a startup, then you should just use whatever you have right now and make your millions or billions. But in terms of long-term scientific impact, I think this is a very interesting direction to see what happens if you ignore the top-down signal like supervision and language and see what happens if you just start with raw data just like natural biological organisms, okay? So this is kind of a bet. It might not work out, but this is the bet that I'm taking. But I think maybe a bigger lesson here is that we need, while we're doing our work, we need to be humble and we need to give credit to the data. It doesn't mean that data is everything. There is definitely space for clever, insights and flights of fancy and beautiful algorithms, but we need to be aware of the power of data and not kind of regarded as second-class citizen, because that way we'll miss some big insights ourselves. Thank you very much.
Thanks, Alyosha, for